Good morning and welcome to the Luminol lab. It's always one of my favorite ways to end the semester, bringing together some of the synthetic techniques that we've learned throughout the semester with just kind of a fun reaction. This is a reaction that happens at reflux, but it needs to be a very high temperature reflux. So we're going to do our reaction in one of these disposable test tubes. And I need to be able to heat it up. And if I just sit it on the hot plate, the heat's not going to transfer very well. So we're going to use one of these thermal wells. It's a big metal block that it will heat up as well. In fact, I'm going to go ahead and just get started. And then that's going to, because the test tube kind of nestles in there, nestles in there, we get a pretty good thermal transfer. Another way you could do this would be a sand bath. That works as well. But we're going to work with this. Okay, so what we're going to put in here is 3-nitrophthalic acid, and about a gram. I have pre-weighed this, and so I will post the data as always. I'll get this transferred over here. Okay, as always, a little bit left over, so I'm going to use my solvent in a minute to transfer it. All these things that affect percent yield. All right. And what we're going to do is we're actually going to use 8% hydrazine. This is hydrazine in water. It's an aqueous solution of it. And the hydrazine is necessary for our reaction. Now, hydrazine is a really interesting compound. It's actually rocket fuel. So we're going to be mixing rocket fuel in here and heating it up. Hopefully this won't be more exciting than it's supposed to be. As I say, it's going to be at high temperatures. Later on, we're going to need some hot water, and if you look around the back, you'll see that I've got some hot water started here. But we're going to put in 2 mils of the hydrazine. Now, this is kind of both of our solvent and our one of our reagents here. 2 milliliters. I'm going to use that to swish and transfer over. Okay. So right now, I've got my hydrazine and my 3-nitrophthalic acid here. And what we're going to do is we're going to start to heat this. And we're going to heat it until we get it to dissolve. So you can see that right now, definitely not dissolved yet. Okay, so let's go ahead and crank up the heat a little bit here. And we're going to watch. Ooh, exciting. I'll think about fast forwarding this part. I'm going to note down what I've done though. Always take good data in your notebook. Okay, so we've got 1.01 grams. Okay. The next thing we're going to add to this, we aren't dissolved yet, but just want to get ready, will be triethylene glycol. This is our solvent. It's very, very thick. It's very high boiling. It's actually related to what we use in antifreeze in your radiator. If you live in an area that gets warm, something like that. Are we getting warm? We are getting warm. It's one of those things. It's always a good idea to make sure your hot plate's plugged in. Almost there. Okay, we're back. So we have now melted all of our material and dissolved it. So we're going to add 3 milliliters of the triethylene glycol, really high boiling material. Okay, so add our 3 mils, and this is going to allow us to run the reaction at a very high temperature. And we have a small problem, and the problem is that we started with 8% hydrazine in water. So we've got water in here, and water only boils at 100 degrees, but we want to get this actually up to 215 degrees. So what we're going to do is we're going to boil the water off, and we needed it to dissolve the hydrazine initially, so that got it into solution, but then we're going to boil it off, and we're going to get a reaction to go. So in theory, I should just be able to crank this up. Remember, a lot of heat is lost to the surroundings. But I have a small problem, and you can actually see it happening right here, which is that as the water is coming up the tube, it's condensing. And it's condensing and then dripping back in. So I need to get rid of the water. So what I've got is an aspirator which is a very fancy name for a bent glass tube. And what I'm going to do is I'm going to set this glass tube in here, and I'm going to hook this up to a vacuum. And so it's going to suck the air vapor out. Now I'm going to clamp this, and I'm going to clamp this because you'll notice this tube is long enough. If it goes down into the bottom, instead of sucking out just the water vapor, it sucks out all the product. I know this because the very first time I tested this lab, I kind of sort of did that. So we can just kind of set it like this, but there's a good chance that, as I say, we'll end up having it slip down. Okay, so we're going to get pretty crowded around here. But I'm going to put this tube in. Take it off here first. Okay, oh, that's a little too far down. Wow, today is just not my day for putting tubes in. Well, I can put the tube in. The problem is clamping it, so I think. There we go. Doesn't have to be a hard clamp, but what I really need is a taller. I need a taller plastic or a metal thing in the back. All right, I got to move this back a little bit. Now we want to monitor the reaction. You can really see all that water vapor forming in there now. Let me bring it a little closer. So I'm going to turn on the water aspirator. So water comes out here, creates a vacuum, starts to pull it out. And I only need to go until I boil off the water. And then I kind of need to measure the temperature of my system. So I've got one more thing I'm going to clamp in here, and that is a thermometer. Because I want to monitor the reaction. I don't want to go overboard on my temperature. Now we could just set the thermometer in here, but there are a couple problems with that. One is that actually puts the thermometer on the very bottom of the test tube, which may just be measuring the hot plate temperature. And we want to measure the liquid temperature. And also it can rattle around and cause problems. So you won't be able to read this from where you are, but we're already at 85 degrees now. Oh, going up about 88, 90. Okay. So crank that up a little bit. So once again, now you can see there's much less water vapor condensing. A little bit's condensing in the tube, but as the vapor comes up, it's getting sucked out. You actually can see some of it condensing all the way up here. So this allows us to remove our lower boiling solvent, because really what we've had is a two-solvent system, where we had water and we had the triethylene glycol. Get rid of that water, and we can now go to a higher temperature. Okay? So we are currently at right about 100 degrees, about 98 degrees. We have added the the aspirator, the thermometer. Okay. So we're going to wait until we get up to about 120 to make sure that we really got rid of all of our water. Now, you keep seeing me duck down. One of the things with these fume hoods, when I'm working with something that I actually need to capture the vapors on, I have to keep the fume hood down quite a bit. Actually, our biggest hazard in this particular experiment is how hot this silly thing gets. Now, later on, after it's been going for a while, we're going to need to remove this. Wow, I can just feel the heat from here. We never grab the tube. The tube's going to be up to like 200 degrees. Instead, we're going to move it by moving the clamp. And by that point, I'll be able to get rid of the other things that are clamped on here. All right, we're at 125 degrees, so I'm going to go ahead and turn off my aspirator and get this out of here. Okay. So I'm still seeing boiling, but what's boiling now is the triethylene glycol. I don't like that we stalled out. I think there may be some water in here. So I'm going to try to suck out any water vapor that we've got. And we don't leave the hose in here the full time because we are actually trying to run a reflux, triethylene glycol reflux. And so we don't want to just suck off the vapor. the solvent you want. Then it'll go to dryness if you do that. All right, 160, there we go, we're climbing up. That is weird. Now, one of the things you should be thinking is, wait a minute, Dr. Mulford, water boils at 100 degrees Celsius. How can you be out at 150 and still have some water in here? And that's because solution down there is very different temperature than the temperature up here. And, as I said, ethylene glycol can hydrogen bond with the water and can form a solution. It does all sorts of weird things. All right, 190, we're getting there. I'm just curious. The hydrazine that I used today is a little bit old, so that may also be part of this. All right, so we are over 200 degrees by 205. Now we're going to go for 2 minutes. 215. A little high. If I need to, I can raise this up a little bit. We want about 215 to 220, so we're at 220 now. I'm going to drop this down in temperature. Oh, starting to go a little high. So I'm going to lift this just a little bit again. I'm using the clamp to lift it. I am definitely not touching that with my fingers. There we go, 225. Sometimes it's a fine line of balancing in between these. So we're going to let this go for 2 minutes. Then we're going to lift it out and we're going to let it cool down to 100 degrees. And after it cools to 100 degrees, we're going to quench the reaction. We're going to stop the reaction going by adding that 15 milliliters of hot water that's heating behind you there.